3.4. Now, when we were going over the homework, I gave a perfect example of what an inverse is, right? That was an accident, it wasn't intentional. But if f of x is equal to 1x, g of x is also equal to 1x, they cancel each other out. When you put, let's say you put 2 into here, you get 1/2. When you put 1/2 into here, you get 1 over 1/2, which equals to 2. You just cancel everything out, okay? Or the example I gave you with Jason cutting the paper in half, Shogo taping it back together perfectly, cancel each other out. Now, if you keep giving the same input to Jason, you cut it in half, cutting half again, now you have these shreds of paper for a party, right? Then you give Shogo paper again, and you keep taping it together, it becomes this big poster. So they do something themselves, but when you put the two of them together, and you take the output from Jason, give it to Shogo, or you take the Shogo's output and give it to Jason, nothing happens. Right? You can give Shogo 2 pieces of paper, he tapes them together, and give it to Jason, he cuts it in half. They are the inverse of each other. Okay? And you heard about this term inverse before. When do you hear the word inverse? What are inverse? What are 2 things are inverse you learn in math?
It's like when you flip the fraction.
Flip the fractions, right? 2 and 1/2 are known as inverse operations. 2x and 1/2 x cancel each other out. 1 doubles it, 1 divided by 2. This is actually, so this would be Shogo, and this, cutting in half, would be Jason. Or other inverse operations that you know. Most obvious one. I'm sure when you're in 2nd grade, you go, oh, I'm learning an inverse operation.
Add and subtracting.
Add and subtracting, right? X plus 3 and x minus 3 are also inverse operation, which means these are inverse function, right? If I give you 4 plus 3 becomes 7, I take that 7, put it into g, 7 minus 3 becomes 4 again. Nothing happened. Okay? So, when you look at inverse function, what we're doing is that we're taking the original relation. Remember, a function is a relation, not an equation actually. I know yesterday, a couple of days ago, we said equation. Function is actually a relation where every input has exactly 1 output. Okay? Relation is simply taking 2 kind of data, let's say height and income, and try to draw some connection to it. So an inverse relation is simply taking, for example, we did a research on height and income. Now we want to know, okay, Brian makes $70,000 a year. Let's get how tall he is. Okay? So we're doing an inverse function. Does that make sense? Taking inverse and input and output and then flipping them. The simplest way is simply taking your x value, changing to the y value, take your y value, pretend like it's x value, and you have your inverse. Okay? So if you have this point before, let's say blue is your, well, that's confusing because I just add a red dot to the graph that has red. Go away. I'll use green. So this is your original point, which is 1, 4. Your inverse is now this point, so that's 4, 1. That make sense? If your point is this point, which is 2, 2, your inverse is 2, 2. It doesn't change. If your original point is 4, negative 2, now you have negative 2, 4. Okay. Notice what's happening here. Okay. This point goes here. This point goes there. This point doesn't change. This point goes there. This point goes there. What's the pattern? It's flipping over the y equal x line, or the 45-degree line. Why? Because that's the inverse. That's actually the inverse line. Whenever you have an inverse function, it would be a flip over that line. Okay? And really, if you think about it, you have your graph is set up to be x and y. And this is why I keep telling you on the test that it's very important that you label x, y in your scale. Because if you flip the x and y, you can actually graph things like this. But whoever used to be here now goes over here. Whoever used to be here now goes over there. And that's why the flip is a 45-degree line. Yes?
If you do the graph on the right, would you still write it on the point
Right,
x,
so
y?
then you would say the inverse function, you would still call this x and y. It's the function itself that you flip. Okay? So in the example, we have find the equation for the inverse relation of y equals 3x minus 5. To find the inverse function, you simply switch the x and y. So this, you would write x is equal to 3y minus 5. And forcing my inverse function to flip x and y, I'm going to write it as a function again by isolating the y. So plus 5 on both sides. X plus 5 is equal to 3y divided by 3. I have y is equal to x plus 5 over 3. So this inverse function is the inverse of the original y equals to 3x minus 5. Wherever you plug in here, and the output you plug into here as input, you get the same number that you start out with. Thumbs up, sideways, down. Oh, wow. Okay. This example I already showed in the when we went over the quiz. The one I gave you was how f of x equal to 1/2, g of x is equal to 1/2, 1 over x, and how g of f of x is equal to x. That proves, also you have to do it to the other way, f of g of x also equal to x. When you can do that, basically you have proven that is your inverse function of each other. If I can give a piece of paper to Jason, and Jason give it to Shogo give it to me back, it's the exact same thing. I go, okay, let's reverse the process. Give it to Shogo first, Shogo cut it in half, give it to Jason, he taped two together, he cut it back in half and gave it to me, and it's still the same thing. Then I know that it's true. Both of them are inverse of each other. You have to go both ways. Okay? I can't think of one example right now where it goes one way but not the other way. But you do have to check both ways. Then you can prove that they are inverse. And you write it with a -1 to show that you're writing the inverse function. So to check that these two are inverse of each other, you do the f of f inverse, or inverse f of f. You plug it in, simplify. You want to have x at the end. And you know it cancels each other out. Okay? For sake of time, I might have to end there. Let's see. Yeah.